Thank you very much. Thanks for having me here. The talk will be about the problem with this so-called vestigial order, and it will touch upon the issue of nematicity. We have seen in the beautiful talk from Peng-Cheng Dai already lots of aspects related to nematicity today that is of relevance for the iron-based superconductors. I will discuss those systems, but also go a little bit beyond them. The work was done with a large number of collaborators, but most specifically, what I will be talking about today was done with Rafael Fernandez, who's going also to be the next speaker, and Peter Ort from Iowa State. So this is an old story, at least where it starts on if you wanted to understand ordered states. And in a way, we have an abundance of those. 81 years ago, Landau gave us a scheme to rationalize ordered states, phases of ordered matter. And he told us that, for example, in the context of structure phase transition, if you have a density distribution, then you need to understand the irreducible representation of the high temperature group to analyze all possible broken symmetries. And a particularly interesting situation happens, as we will see, if you have so-called higher dimensional irreducible representation. I mean, a triplet superconductor is a very natural example for this, so this is nothing that is super new to us, but it is something that was very, very beautifully put together in this 1937 paper, again, 81 years ago. So now, if you have such an order parameter, very often it is hesitant of actually ordering, or its ordering is suppressed in one way or another. Fluctuations and frustrations are the key words here. And you have a number of options that could happen. So suppose my order parameter doesn't want to order, or at least its transition temperature is to some degree suppressed compared to what you would naively expect if you estimate the energy scales. Then there's two options. One is, well, nothing orders ever. You have what we would call a liquid. A spin liquid is an example in mod insulators, where spins just don't order altogether. Or another option would be just copper or sodium. It doesn't become superconducting because there's a frustration between the Coulomb interaction between the electrons and the Coulomb interaction between the electrons and the ions. So these are systems that remain liquids. On the other hand, we can, if the order parameter itself doesn't want to order, we could maybe make a compromise, and a higher order component version of the order parameter could order. For example, if the order parameter I use here, Landau's notation, eta, doesn't want to order, maybe we can find some combination of the order parameter where we have quartic or third order terms that individually break a symmetry. For this, of course, to happen, this must break a symmetry, otherwise it would at least not be a natural second-order transition. And in addition, for this to make sense, there has to be some energetics involved that supports that state. In all cases, as it is a higher-order composite of the original order parameter that is just being suppressed by fluctuation or frustration, it is still a leftover of this order parameter. Although this doesn't order, or it only orders at lower temperature, it's a vestige, a leftover, and that's why I think this term goes back to Steve Kivelson. We call this situation vestigial order. Now, the iron-based superconductors are probably by now the best understood representations of this realization of order. And so again, you had seen the talk, but I'm flashing through this quickly here. We have a magnetic phase, we have a superconducting phase, we have a phase transition of the magnetic phase, and in the magnetic ordered state, we have essentially two competing ground states that are not symmetry equivalent. So in one case, we have ferromagnetic ordering along one direction and antiferromagnetic along the orthogonal, and then we have exactly the rotated version, ferromagnetic along this direction, antiferromagnetic along the other one. And the natural way to write this down is, of course, that you have some spin configuration that can either do this or that, and this is where the multiple componentness enters the game. And one way to construct a higher order object out of this is, for example, to take the square of the amplitude of this state minus the square of the amplitude of that state and take the average. This is a state that would not break time reversal symmetry. However, it breaks a rotational symmetry, and that's why we call it a nematic state. And for example, if you have one or the other, it's just a label, an Ising label for this or that configuration. But of course, this is not the only option you have in that system. You can also build the scalar product, you can build the cross product of those. All of them would be potential candidates for higher order correlation functions that individually break a symmetry and are candidates for new phases. Now, the beauty is that you can then come to the conclusion that this order parameter gets its own individual life. It gets its own life because it has its own phase transition. It doesn't order simultaneously, or it doesn't have to order simultaneously with the actual magnetic transition. So you can break this rotational degree of freedom above the magnetic transition in this state. So where we have a low temperature magnetic state, a high temperature disordered state, and an intermediate state where you already know what the orientation of your spin to the right and in front of you is, even though the spins themselves are not yet ordered. All of this goes back to a pioneering paper from Premichandra, Piers Coleman, and Anatoly Larkin in the early 90s, where they analyzed a specific Heisenberg model where this temperature is even 0. And you still have that Ising transition of that rotational degree of freedom. And a number of people have pointed out that this is important physics for the cuprates, for the iron-based system, sorry. And here we see these two phase transitions, one coming after the other, so we do have such a realization. The upper one is actually a structure phase transition, or at least as such identified. And of course, once you break this rotational symmetry, your structure will know about it. I get to that. In the inelastic neutron scattering, in this intermediate regime, you would then have no magnetic order, but you have anisotropic fluctuation. So one of these Q point is sharp and has a large correlation length, and the other one is actually hardened. This was beautifully seen in Peng Cheng Dai's data using inelastic neutron scattering data. I think now 2 years ago or something, or even longer. So if you have, again, this is the phase diagram, here's a theorist version of it. There's always the option that these two transitions are joined and then they become first order. But it's not really possible, at least when you include seriously fluctuations, that you have two joint second order phase transition. They then tend to be split, and you have this intermediate so-called vestigial phase. If you want to understand the fluctuation of that new order parameter, what you, for example, should look at is the neutron scattering version of spins for the nematic state. And it was pointed out in this paper, Raphael was a co-author, Jan Gallet's data here on the iron-based superconductor, that a Raman investigation in the right symmetry channel, so the Raman response tells you exactly what the dynamics is, and you see the softening of the Raman response as you go lower in temperature in the right channel, namely in the one that breaks this rotational symmetry, as opposed to another symmetry channel. So Raman is exactly the right experiment if you want to measure the dynamics of this object. You can even go further and look at this Magnon coupling or spin excitation coupling in more detail. We did this here in a collaboration with the Rome group, Marco Grilli and Carlo Di Castro, and experimental data by Rudi Hackel, where you can fit quite quantitatively and in great detail the Raman response based on this specific nematic scenario that uses magnetic excitations to drive this symmetry broken state. Now, in this community of iron-based superconductors, there's a theme that appears again and again. It's a very legitimate question. The statement you will find very often is nematicity due to spin or due to orbital fluctuations? I believe, my guess is about 30 papers start in the introduction to pose that question in order then to go about giving an answer to it. This is a perfectly legitimate question, but I think one can sharpen it a little bit to understand and to give a clear answer. Sometimes you want to know, is the electron-phonon interaction relevant for high-temperature superconductivity? This is almost an unanswerable question, because microscopic mechanisms are very hard to pinpoint. Symmetry answers, however, are clearer to state. And so if you look at the statement, maybe it makes sense to reflect a little bit, because orbital ordering, meaning if you have a rotational symmetry, you would naturally have certain orbitals arranged in a certain way, that along a certain direction, the YZ orbital then looks differently than the XZ orbital. That is symmetry imposed and natural. And in that sense, orbital order is nothing else but a realization of nematic order, not causing it, it is it. So therefore, if you wanted to sharpen this question, and I want to give you an answer as we go along, the question that you should be answering is basically, is nematicity vestigial? So is it a secondary object of a primary order parameter, or is it the primary order parameter itself? And then if you answer that question, you know precisely whether it's, in the first case, whether it's magnetically induced, or in the second case, whether it's orbitally induced. Now, why is this interesting? So if we go back to Landau and look at this expansion of the order parameter, then it becomes particularly relevant to break symmetries of composites, so of combined order parameters, if these are multi-component order parameters. So the formal language then is they transform according to some higher reducible representation of the group, irreducible representation of the group. So if I take this order parameter and I just square it up and it's a single component order parameter, there's no symmetry I'm breaking with it. But if I mix it appropriately, for example, the x and the y components of the momentum ordering vector that I mentioned earlier, then I can do this. So what I need to do is I need to look at basically the product representation of the order parameter symmetry group. And if it's non-trivial, then I find those are the potential ordered states that can emerge, and those are the symmetry that can be broken by those vestigial order parameters. So that's a clear recipe. It's straightforward. You just need to look up what was written 81 years ago, and then you can also conclude from there what vestigial states are possible. And then, as I just said, you can conclude that such an order parameter can break its own symmetry if you have a multi-component order parameter. This does not work, for example, for a D-wave superconducting order parameter in the cuprates. It's a single component order parameter. So you need to have, for example, a triplet superconductor. That would work with multiple components. So let's do this for the iron-based systems one more time. So we have a certain group that is a combination of the point group and certain translations, because the magnetic state breaks translation invariance. And if you build the proper group that has been written down by a number of authors in the past, you find that there are a total 3 non-trivial realizations you can have. And exactly one of them is our beloved nematically ordered state, where you break a rotational symmetry. I'm not bothering you with the details of the group theory. It is some web page you can click it all on, and then you know what's written behind those letters. But there are other options as well. And the beauty is, and it was pointed out by Raphael and collaborators before, without this group theoretical analysis, but the beauty is those are all the options you can come up with. One is this famous C4 symmetric state, and there's also a recently seen a state with chiral order in the superconducting state in another class of the so-called 144 iron-based materials. So none of these two states, and they have been observed, would have anything to do with orbital ordering. But they naturally occur from the exact same magnetically ordered state. It's just that certain interaction parameters that depend on doping, band structures, and so forth change their values, and you can prefer one over the other. This seems to be the most frequently observed state, but the other ones, at least the associated magnetically ordered state associated with such a vestigial state, have been observed already. So for me, this is a very strong indication that this concept of vestigial order in these iron-based systems is a very sensible one. Now, the same state also couples to the lattice distortion. I mentioned this earlier. It was initially observed through a lattice distortion. So the order parameter couples bilinearly and therefore induces immediately a lattice distortion. It must so. And if you then, and this was utilized, for example, here by a number of groups. I'm showing data here from Anna Böhmer because it explored so nicely the softening of the lattice around that state. And if you think a little bit about what such an order parameter would do, its own susceptibility, the nematic susceptibility, would then induce a softening of the corresponding lattice constant. That's absolutely normal and to be expected. It is somewhat different from the elastoresistivity, where you look at the change of the resistivity anisotropy with strain. But for our purposes, this is what we're interested in. We see a large nematic susceptibility in a broad range, even coming in some systems to a nematic critical point type of behavior. Now, if you honestly and in detail analyze what's happening, you find that the coupling to the lattice is very sensitive in which phonon directions you're really looking at, and specifically acoustic phonons along high symmetry lines that would couple to this was recently pointed out by Indranil Paul and Markus Garst, and you can also see this in the literature in the 70s and 80s when structure phase transitions were discussed in great detail. Now you can then conclude from this model that it would naturally give you a softening of the lattice and the mean field Curie-Weiss behavior because of long-range strain couplings in the system. That's one thing, that's a theory statement. But you can even go further. You can ask the following question. If I look at the phonon spectrum, it's the same elastic constant that is determined by the nematic susceptibility gives me the sound velocity. The square root of it is essentially the sound velocity. And therefore, and this is a work recently done by the neutron group, here, Dimitri Nesvik and Frank Weber in Karlsruhe and Boulder, you can therefore go a step further and ask of whether indeed the momentum dependence that you see at higher momentum equals that you see asymptotically at very, very low momentum. Basically what you need to take into account that this shear modulus is a Q-dependent object. It depends on the length scale you're probing the system at very long lengths because we are near a phase transition. So we analyze those data and you can basically extract from it the nematic correlation length. So see what is the size of typical nematic regions of that system just from the softening and the momentum dependence of the softening of that acoustic mode. Basically, you use the phonons as observers for nematicity. Something very similar was pointed out by Peng Cheng when he says basically my phonons coupled to those two magnons is basically the underlying microscopics for this softening. Here we used it to determine the length scale, and you see that it's about 30 lattice constants. So this is a huge nematic regions that the system has. This is a really critical mode of that system. Now, with this insight, we can ask, is this something, and that I laid it out at the beginning, that's a bit more general, so that doesn't only have to do with magnetically induced vestigial phases, but could a superconductor do the same? And of course it could. So let's look at a simple example, a P-wave superconductor. So I have now, for example, a P-wave superconductor characterized by this infamous D vector that points in a certain direction, and now I can have a Kx and a Ky state. So we know it could be Kx plus IKY. This would be what many people thought might be relevant with the transform Rosenates, but it could also have two real amplitudes there. Ultimately, we have a two-component order parameter because these two objects can independently take certain values. So you can do the same analysis, and once again, my order parameter transforms according to a certain symmetry group. It's an odd parity state, so it has to be some U up here. And then you find there's three options for that superconductor to form vestigial states. And again, what you find is there are two nematic superconducting states where rotational symmetries are broken, potentially above the superconducting transition temperature or at the latest through a first order transition at the superconducting transition temperature. You could also break above the superconducting transition temperature time reversal symmetry. So it means, and you can look at them here in quite some detail, but it means if fluctuations are in any way sensible in a system, then you will always enter a triplet superconductor through either a first order transition or a sequence of transitions. It is illegal statistically mechanically to go directly through a second order phase transition into a triplet state. Of course, you need to have fluctuations sufficiently important to make the first order jump observable or the width between these two transitions significant. So maybe strontium rusinate may not be the right example, but low density superconductors certainly would be. So, and an example where we looked into this is copper doped bismuth selenide. So here you have a topological insulator that is slightly doped by copper intercalation. You have a very low carrier concentration, and there are all reasons to believe that the superconducting coherence length is maybe 5 times the Fermi wavelength, but not a fifth of the Fermi wavelength. So basically you can assume that this is a correlation length that's of the order of the Fermi wavelength, and fluctuations cannot be ignored. One state that was proposed for the system is an odd parity state, once again, from Liang-Fu and Erisberg, that has, again, a two-component order parameter. Now, because it's an hexagonal arrangement, you need to use a couple of Courtier transformations to get familiarized with what that potential state would be, but in the end of the day, it is straightforward. What was also seen that superconducting state breaks a twofold symmetry. This is night shift measurement data along, for different field direction in that superconducting state, and you see that actually has a twofold symmetry is broken in that system. So we can do the same analysis here again. We have a superconducting order parameter that transforms according to a certain irreducible representation, and for this specific group, there are two options that you can have. You can either break time reversal symmetry in the system above the superconducting transition, or what you can have is nematic superconductivity. Our experiment already told us that this is the case, but you can also do a band structure calculation and actually do a weak coupling analysis and decide which of these two are winning, and we found that this one here wins, and there's a recent analysis that shows if you have very, very thin films of this material, it could cross over to that state. Bottom line is there are two different order parameters. That is, so the vestigial state has again its own richness of order parameters, and you could ask the question whether there's the vestige of the vestige. In this case, it doesn't give you anything new because of the nature of the symmetry group. But what you do find is that basically this phase transition of that state is characterized by a three-state Potts model. A state that is statistic mechanics is well known, interesting disorder effects happen. It should be a first order transition into the vestigial nematic state above TC that could be driven second order by random field disorder effects, but you should see that phase transition on its own right. So the expectation is that then there should be a sliver where we estimated it to be about 10% of TC of a nematic transition above the superconducting transition, a state where this nematic order parameter then is finite even above the superconducting transition, where we have a softening of the lattice that would even be perfectly soft if there was random field disorder in the system, and where we would expect, because it's a fluctuation-driven mechanism, that the Aslamazov-Larkin fluctuation conductance should be anisotropic. So if what you would have to do in this intermediate regime here is to measure the resistivity, which is still finite, that's not a superconductor, and it should have an anisotropy of the resistivity in the fluctuation contribution, and that's what we've calculated here. So give me one last example. I have enough time, I believe. That's a bit of a more crazy example, but it's nice to see how you can play with this without doing any hard work. It's actually a lunch discussion I had with Steve Kivelson when I was visiting Stanford recently. So you have a Cooper pair, and we know a Cooper pair is made out of charged 2e objects. It's actually its own composite order parameter, but in this case out of fermions. Now, we know that this gives rise to flux quantization where there's a 2e written down here, and if you look at the AC Josephson effect, again, the 2e is clearly visible and non-negotiable. And what you can also ask the question is then whether there could be a state that has charge 4e superconductivity. It has been discussed, it has been proposed, and mostly in the context of situations where you have so-called pair density waves, a density wave that interferes with the superconducting state and forms a new state of order. Beautiful stuff. What I'm proposing here is something completely different, very, very simple. Take a triplet superconductor and do an artificial analysis where we have no spin-orbit interaction. We're living in 2 dimensions. If I have a triplet superconductor in 2 dimensions and no spin-orbit interaction, the order parameter is a 3-component vector. As such, it's not allowed to order. It's a vector that is completely rotationally free. It's even a complex vector, doesn't make it better to want to order. And you can ask the question, it cannot order itself. These objects all can't order because they're all vectors themselves. And therefore, if you've grown up like I in a dictatorial environment, you know everything that's not forbidden, that is compulsory. So therefore, the only object that is really not forbidden as an ordered state is if you build the scalar product of these triplet order parameter with itself. This is a singlet in spin space, it can order, but as there's no star up here, it will break gauge symmetry, but as there are 4 fermion operators behind this, because ETH already has a pair, it's a charge 4e superconductor. And you find that this is a legitimate and actually the only ordered state, and you can calculate its ordering temperature, and it will enter the system through a Kosterlitz-Howells transition. If you then increase the spin-orbit interaction, you find that there's at least a regime of finite spin-orbit interaction where that funny state is stable. It's a bit academic, but it's at least cute, and again, you don't need to do a lot of work to see such a pretty cool order parameter, right? So you have Cooper pairs that pair up to form a 4E superconductor. I could give you another example, but I'll leave it there and rather summarize that multi-component order parameters and some frustration and fluctuation in the system can actually give rise to funny stuff. It's good old-fashioned Ginzburg-Landau type analysis, but you look a little bit at fluctuation effects, you find that the fluctuations start to order and break individual symmetries, and then when you go through all the details, and we have recently summarized this in a little review article, you find there are lots of options to give you rich phase diagrams, not because you have a microscopic understanding of the underlying model Hamiltonians, but just because the symmetry enforces it to be that rich. Thank you so much.
Jörg, thank you very much for this nice talk and for finishing on time. Yes, please.
So the natural question, of course, about iron selenium.
Yes.
Can it be vestigial order? But I would add the more interesting for me to ask about what could power the vestigial order. For example, if one accepts that the main order is powered by Fermi surface nesting, then for vestigial order it should be different vector, and it could be the origin for it, right?
First statement about iron selenium. Iron selenium is a funny system because here the primary order parameter, if the story I just presented to you is correct, is hesitant to order itself, right? But that is in a way, and it's presumably not because the system is in any way two-dimensional, and there's some Wagner theorem suppressing that order. There are ultimate reasons, many reasons that this is not the case. In my view, it is probably because the system is more in a strong coupling regime than many of the other iron-based superconductors. If you look a little bit, you get that vestigial phase when you have a threshold correlation length of the primary order parameter. The calculation where you can make something like a controlled statement is when that length scale is large. That's when recoupling calculations make some sense, and we can talk about nesting, or we can talk about calculations that we can do. If in this system, my view is that the correlation length is of order 1, maybe 3, I don't know, right? When this transition takes place, it takes all control from me as far as an order parameter-based description is concerned. There are alternative strong coupling niche versions of that. For example, one by Andrei and Raphael, where they talk about Pomeranchuk type instabilities that would basically be the more natural description of that same state, however, in the strong coupling regime. I personally find it surprising that this one system should be orbitally ordered, but I find this, but this is a personal opinion. One last statement on iron selenium. If you look at the anisotropy of the resistivity as function of temperature, before iron selenium was even investigated, we predicted how it would look like in a system with that vestigially ordered state when the nail temperature was 0. And basically the data lay on top of a calculation that was done something like 3 or 4 years before the measurements were done.
Jörg,
yes.
This is not about iron selenium. It's about the last part of your talk. So suppose you take this 4E superconductor,
yes,
and suppose it's uncharged. So what do you have for collective modes? Do you still have Anderson-Boголюbov?
Yes.
So there are phase fluctuations.
Yes, there are phase fluctuations, if it was uncharged.
Next question. You have a question?
Presumably, so the structural transition is presumably, has a well-defined temperature. So
yes,
how do I understand in a phenomenological sense what is that temperature? So if I have an ordinary Landau free energy, how do I calculate, in which I have the usual terms, how do I calculate that temperature?
Yeah. Statement number 1, yes, there's a sharp temperature. It's precisely the same temperature where we talk about the situation that we have a vestigial order parameter. These two objects can hardly be distinguished at first glance, I always thought. So how would you do this? The idea came from Ian Fisher, who proposed the measurement of what is called elastoresistivity. So what you do there is you take the resistivity anisotropy as a placeholder for the order parameter of whatever is going on there. And what you build is you do the Legendre transformation of the theorist in the laboratory. You do it always at zero strain. So you tune your system to a situation where you do not have that deformation. Then you take the derivative, the order parameter d strain. If the order parameter was strain, the result would be 1. What he finds is a cusp, a very sharp structure, very much in agreement with the fluctuation seen in the Raman spectrum. There's only one interpretation to my mind. That means it's something else but the lattice that is going on. So we are saying if I were artificially to keep the lattice constant and fixed in place, there would still be a phase transition. I never thought that this was doable in experiment, but Ian Fisher showed that it actually is.
Okay, Philip, please, a very brief question.
When your charge is 4,
Yes.
what is U1 broken down to?
Wow, because you cannot do an arbitrary gauge transformation.
Well, we understand 2. It's U1 down to Z2. What is 4?
It is U1 down to Z2, and here it would...
That's impossible.
I simply don't understand the statement, to be very honest.
We know that superconductivity, you go from U1 down to Z2.
You can write down a topological field theory for a superconductor if you include long-range Coulomb interaction that would be characterized appropriately by a Z2 object. That's what you're saying.
Right.
Right.
So
yes, but these effects, as we all know, become relevant when the system is of the size of the universe. So the transverse fluctuations of the electromagnetic field included means there is no superconducting phase transition. We all know this. But for all practical purposes, a superconductor is smaller than the size of the universe, and then we can observe it.
Okay.
You're quite right.
So, Jörg, thank you very much for your answers. I propose to continue in the break.